This series of 3 videos discuss correlation. This first video focuses on covariance and the different types of patterns one can see in bivariate data. Correlation involves examining what is known as a bivariate association, which means that we're looking at the association between two variables simultaneously. These can be things like the relationship between someone's height and weight, how tall they are compared to how much they weigh, or it can be something like how many hours a child reads at home and his or her verbal PSAT score. Typically, the two variables are both characteristics or measurements based on the same individual. For example, how well do high school students perform on the PSAT in relation to how much they read each week? But it can also involve characteristics across pairs of different people. For example, a colleague of mine previously examined mothers and daughters' impressions of parenting behavior in the home. You can look at the correlation between something like the level of support that the daughter reports and the level of support that the mother reports. Correlations like this can be presented visually using a scatter plot. In a scatter plot, each pair of scores are represented by a single point based on values of one variable along the x-axis and values of the other variable along the y-axis. For example, let's say that I want to make a scatter plot of student verbal and math ability based on a standardized test. We'll assume the first student has a verbal score of 122 and a math score of 135. We'll start with the verbal score of 122 and move along the x-axis until I reach 122. I then use the math score of 135 and move straight up the y-axis until I reach 135. I then place some mark at this point, and this mark represents both scores for the first student. Okay, now let's assume the second student has a verbal score of 65 and a math score of 81. We start with the verbal score of 65 and move along the x-axis until we reach 65. We then use the math score of 81 and move straight up the x-axis until I reach 81. I then place a mark at this point, and this mark represents both scores for the second student. Now, if I've randomly selected a group of students and I plot all of their scores, we'll often see a shape or pattern such as this elliptical form. It kind of looks like a tilted potato. Notice that there's a trend in that higher verbal ability is associated with higher mathematical ability. The overall trend isn't perfect, but there is a general pattern of higher math scores with higher verbal scores. Here's another example of a similar pattern. This ellipse illustrates the general shape that one might expect to see in a scatter plot of parent education and child reading ability. We call this a positive association because as parent education scores increase, child reading ability also tends to increase. In contrast, this ellipse illustrates the general shape that one might expect to see in a scatter plot of the number of absences a student has in a school year and his or her academic performance. We call this a negative association because as student absences increase, academic performance decreases. Alternatively, you can have no association. For example, shoe size and academic performance. Big feet, small feet, it really doesn't matter when it comes to academic performance. There's just no association between the two. Now, sometimes you can have a more complicated association, such as a U-shaped relationship. For example, in a previous line of research, I examined the curvilinear relationship between adolescent problem behaviors and levels of parental control in ethnic minority families. Specifically, adolescent problem behaviors tended to be higher when parental control was either very low or very high. Behavior problems were lowest at some middle level of control. These sorts of U-shaped curvilinear relationships can be a normal U or an upside down U, and may reflect a strong association between the two variables, but it's a nonlinear relationship, meaning it doesn't follow a straight line. These sorts of associations are more complicated and we won't cover them here, other than note that you can have a nonlinear relationship. But we'll get more into that when we move on to multiple regression. Now, beyond simply describing these as a positive or negative or no association, we can also calculate the covariance and correlation between the two variables that also indicate their strength of any association. Now, you may see the actual covariance or correlation formula written a number of different but equivalent ways. And while there are computational formulas that are easier and quicker and fewer steps if you have to do the calculations by hand, given that software will do that for you, we'll stick with the more transparent and intuitive conceptual formulas for now. Let's begin with the covariance. Remember, the variance of a variable, say x, using the descriptive formula is the standard deviation squared. It's written as capital S sub x squared and is equal to the sum of squares for x, or the sum of x minus x bar squared, all divided by n. Similarly, the variance of y is written as capital S sub y squared and is equal to the sum of squares for y, all divided by n. Now, look at the variance of x again. Notice that the numerator is x minus x bar squared. X minus x bar reflects the variation of individual scores around the mean. It's squared, so you multiply it by itself. And you can think of it as how much individual scores vary with themselves. In contrast, the covariance can be thought of as how much two variables vary together. To see that, let's look at the covariance formula. It's written as capital S sub xy and is equal to the sum of x minus x bar times y minus y bar, all divided by n. So notice a few things. Instead of squaring the x deviations or squaring the y deviations on their own, the covariance multiplies the x deviations by the corresponding y deviation for each person. This is called the cross product. The cross products are then added up for each person and divided by n. By calculating the cross products for each person's deviation on x times their deviation on y, adding them all up and then dividing by n, you can think of the covariance as the average of the cross products. So the larger the covariance, the more x and y are deviating or varying around their respective means together. Finally, notice that for variance, the notation is s sub x squared or s sub y squared. But because the covariance is calculated on the xy cross products rather than the deviations of x squared or the deviations of y squared, the notation for the covariance is just s sub xy because it's the deviations for x and y and it's not squared. To understand what that number, what the covariance reflects, what it's telling us, it may help to visualize what happens if someone's x and y values fall above or below their respective means. Here's a diagram where we've taken an example of two variables with a positive association and divided it up into 4 quadrants based on whether a person's x and y scores are both above the mean or whether their x and y scores are both below the mean or whether they are above the mean on y but below the mean on x, or whether they're below the mean on y but above the mean on x. Notice that for each of these quadrants, we've indicated whether the corresponding cross product is going to be positive or negative in value. Now, if there's a positive association, we would expect to see relatively more scores in the quadrants for both scores being above the mean and both scores being below the mean. In both of those cases, the cross product, the numerator in the covariance formula, is positive. At the same time, given a positive association, we would expect to see fewer scores in the quadrants where one score is above the mean and the other score is below the mean. In both of those cases, the cross product is negative, so we would see fewer negative cross products. As a result, the value of the covariance will be more and more positive the stronger the positive association. The same pattern applies to a negative association, but in the opposite direction. The more negative the association, the more cases we will see in quadrants where the cross product is negative, and the fewer cases we'll see in the quadrants where the cross product is positive. As a result, the value of the covariance will be more and more negative the stronger the negative association. But the problem is that the covariance is in the raw units of whatever x and y are. So it can really take on any value from positive infinity to negative infinity, depending on what the units and scaling are of for x and y. We need to somehow standardize the covariance so that its value has similar meaning regardless of whether we're measuring something in meters or miles or hours or seconds. We'll cover that in our next video. Okay? Bye for now.